Fine, so today we are going to revise third chapter, that is current electricity. We will begin with the definition of electric current and what is meant by steady and unsteady currents. Okay, now the definition of electric current will be flow of charges. Simple, flow of charges. Okay, or movement of charges from one location to other. Ata, how can the charges move? The charges can move only when there exists an external electric field. Correct? So if there is a point A here, let's suppose, and suppose there is another point B here, then the charges can continuously move in this direction. Okay, well, depending on what sign the charges have, but let us assume that all of them have positive charge. So whenever there exists an electric field here, the charges will move in that direction. Or suppose this is VA, the potential at A, and suppose this is VB, the potential at B. So whenever VA is greater than VB, the positive charges will move from A to B. Okay, positive charges move from A to B. Is that clear? Okay, so what is electric current? We define electric current as the rate of flow of charges. Okay, so although we said here flow of charges, we say current is actually the rate of flow of charges. Okay, so suppose during a time interval of delta t, okay, during a time interval of delta t, delta q was the total charge flowing or flown. Then we define the current I as delta q by delta t. And if for same lengths of delta t or same period delta t, if delta q changes, okay, म्हणजे एका delta t साठी delta q काहीतरी आहे suppose q1, and suppose for some other delta t interval, let's say delta q is something different, then that refers to as unsteady current. And in unsteady currents we can define the actual current as, so this is for steady, okay, this is for steady currents, and if the current is unsteady, then I is defined as the limit of this as delta t tends to 0, and that is nothing but the derivative of q with respect to time. Okay, I hope you understood this, the steady and the unsteady currents. Understood? Okay, so roughly if dq by dt is constant, roughly if dq by dt is constant, then it will be steady. And for any other function q, if dq by dt is not constant, then unsteady current. Okay, then unsteady current. It is also interesting to note here that you cannot have a repository of infinitely many charges at point A. Okay, so instead of sending all available charges from A to B in a very short span of time, what we do is we actually circulate the same charges one after the other. Okay, so there is a pumping mechanism, so to speak. There is a pumping mechanism which helps us in doing that, and that pumping mechanism is our energy source. And for us in this chapter, that energy source is going to be a battery. Okay, that energy source is going to be a battery. Right, that energy source is going to be a battery. So what is the job of battery? The battery actually establishes the electric field inside the conductor. Okay, and it also therefore pushes the charges, okay, through it. Okay, so battery, and the terminal potential difference refers to the potential difference between the terminals of the battery. So this is delta V, or terminal potential difference. We will discuss this again, but just to give you the analogy, the cell is actually going to circulate the charges so that you get a steady current. Okay, all right. Then Ohm's law. What is Ohm's law? In the school version of Ohm's law is the following. Okay, the school version of Ohm's law is the following. Uh, in a circuit, made of metal wires. Okay, in a circuit made of metal wires, the ratio of delta V, potential difference between two locations, and the current I is constant. And we generally call delta V as V itself, the potential difference, the way we do it for capacitors. And when we say that delta V and I is constant, okay, that constant is called as resistance. Okay, that constant is called as the resistance of the metal. The SI unit of resistance is volt per ampere or ohm. Okay, so this is the school version of Ohm's law, which does not take into consideration the physical origin of resistance. Okay, and the physical origin of the resistance is the metal ions, okay, which are formed and they cannot move due to the strong bonds between them, and the electrons in the outermost shell being relatively free are called as conduction electrons, which are free to move, and due to the collisions between the ions, positively charged ions, and the uh, electrons find it difficult to reach to the other location, and that is the physical origin of the resistance. So in the college version, in the junior college version of Ohm's law, we actually take into consideration all of those things, and we arrive at a slightly different version of Ohm's law, where we define two new things. The first one is called as current density, J bar, which is a vector quantity. We relate it to E bar. There also exists a proportionality relationship there, and that the constant of proportionality is called as a conductivity sigma, and the reciprocal of that is resistivity, which is related to resistance. Okay, so let us move on. Delta V is the potential difference between the two locations. Okay. It is change in potential difference, but we often drop delta and just say V. So when we say V equal to IR, anyways we are always interested in potential difference, right? Even when we had defined potential or potential energy, we are interested in that. Okay, anyways, yes. Okay. Then let's talk about resistance and resistivity. Okay, so resistance, okay, resistance, which is the constant of proportionality on the current side here, V equal to IR, the more familiar notation. Okay, V equal to IR. It is found to depend on two things. Okay, the resistance of any substance, metals here. Resistance is found to depend on two things: the geometry and the material. Okay, in other words, if I take an extremely thin wire, okay, if I take an extremely thin wire and connect it to a battery of, let us say, 2 volt, okay, and if I now take a cube, okay, if I now take a cube of the same material of which the wire is made of, and suppose to this cube I again attach a battery here. Okay, suppose I attach the battery here, And if I measure the current flowing through the wire and the box, then I will find that they will be different. Okay, it's hard to sketch the current here, but let's say call it I2. So I1 will not be equal to I2. A proof that resistance depends on geometry and material. Okay, it's a thought experiment, but you can actually do it in a laboratory. Okay. Whereas resistivity denoted by rho is what? Is a material property only. Material property. So it just depends on material. So resistivity of copper will be same whether you take it a wire, so in the wire form or in the ball form, any irregular shaped form, or even this cubical form. Okay, so resistivity is a material property, resistance is a material property as well as a geometrical property. So resistance depends on shape and size, resistivity does not. Is that clear? Okay, so if I call this iron block, iron wire, and suppose I call this iron block, then what will be same for both? Resistivity will be same. Resistivity of iron wire is the same as resistivity of iron block, but in general the resistance of iron wire will not be the same as resistance of iron block. Okay, and how can we prove this? If we connect both of them across the same battery one by one, and if we measure the current, then we will find that I1 will not be equal to I2. Okay, now are the resistance and the resistivity dependent on each other, or rather does the resistance depend on the resistivity? Of course it should, and the connection between the two is given by R equal to rho L upon A. Okay, R is given by rho L upon A, where L is the length of the substance or length of the object measured in the direction of the current flowing. Okay, so in this case L1 will be this much, L1 will be this much, and L2 will be this much. Okay, understood what L1 and L2 are, what basically L here represents? L represents the length along which the current flows. Is that clear? And what about area A? Area represents the cross-sectional area through which the current is flowing. So this is A2. And for this wire, if I zoom in here, then this will be my A1. So clearly smaller area, larger the resistance, larger area, smaller the resistance. Okay, so if I were to compare the resistance of iron wire to resistance of the iron block, then okay, I would be looking at this one. So I'll be looking at L1 upon A1 divided by L2 upon A2. So if I know the actual numbers, I can figure it out which one of them will have larger resistance. Can you tell me, will it be an iron block or the wire with greater resistance? It's wire because its area is extremely small, okay, compared to the block. Okay, fine. So we now define a new term called current density. Okay, so current density J bar when dot multiplied with area. Now in this case area is a vector, very much like how we treated area to be a vector quantity in defining electric flux or even magnetic flux. Okay, so this is the current. So if I take an area A, okay, and suppose the current is flowing in this direction, then the current is related to this area A through which it is flowing, because see, current is, although we show current by arrows, it's actually tiny charges which are flowing individually. Okay, it's not that like water. Even in water, we have molecules flowing, but they're so large a number that we consider water to be a continuous fluid. Okay, same thing is to be understood or to be kept in mind when we are talking about electric current. Now, if the current is not steady, in that case we define the electric current as the integral of J bar dot dA bar. Okay, we define it as integral of J bar dot dA bar, where the integral is taken over this particular area. Okay, now at the beginning we mentioned that unless there exists an electric field, the charges cannot move on their own, right? So this electric field, which in this figure is being provided by the battery, that electric field's strength also decides how much current is flowing, okay, or how much current will rather flow in that particular conductor. So what is the relationship? We can derive it. We won't do it right now. The relationship is that the current density J bar is found to be proportional to electric field. Remember, these are vector quantities. So the direction of current density is in the direction of electric field. Always remember that. Same direction. Same direction. Okay, because sigma, that is conductivity, is a positive quantity. It cannot be negative. And the relationship between conductivity and resistivity is that rho is equal to 1 upon sigma. Okay, rho is equal to 1 upon sigma. So they are inverses of each other. The resistivity and the conductivity, they are inverses of each other. So you may write Ohm's law as V equal to IR. That's the school version. That's right. But you can also arrive at a more general version of Ohm's law. That's the college version, and that is J bar equal to sigma E bar, where J bar is the current density whose integral taken over an area through which the current is flowing is the current. Okay, so current has now been defined as a surface integral. Okay, so J bar is a vector quantity, current is a scalar quantity. You can define current as flux of current density if you want to call it flux of current density. Just like flux of electric field is E bar dot dA bar. Okay, with that. Alright, so we have defined current density, we have defined conductivity to be the constant of proportionality, a scalar constant of proportionality on the electric field side in this relationship, and E bar is the electric field inside the conductor. Okay, now let us move on to the inner picture. What exactly happens if when we say that current is flowing through the wire? Okay, we have noted this earlier that even when there is no potential difference between the ends of a wire, so if I just take a wire and connect it like this, okay, even in this wire electrons are moving with very high speeds. Okay, are moving randomly, electrons are moving randomly with very high speeds. We have noted the order of magnitude of the speeds, okay, with very high speeds. But okay, but if I connect a bulb here, the bulb will not glow, and the reason why it will not glow is the net velocity of the electrons. If you take the average, it is zero, the vector addition. Okay, it will be zero. Now what happens if electric field is established in the wire? Okay, after E bar is set up, okay, after E bar is set up, each electron will drift from its random path. Okay, each electron will drift from its random path. Why will it drift? It will drift because of the application of electric field. So if we now take the same wire and join a battery here, Please remember, the purpose of the battery is to create an electric field inside the circuit. Okay. So after electric field is set up, each electron will drift from its random path, giving rise to current. Giving rise to current. And the drift speed is very small, if you remember the drift speed. So what is actually the drift speed or drift velocity? Drift velocity Vd, okay, drift velocity Vd is defined as the average drift speed or velocity, average drift velocity of all electrons, of all charge carriers. Okay, and this will be the same. Okay, this will be the same, although electrons will be having different individual velocities. This is average drift velocity. Okay, what is tau? Can anybody tell me what is tau? We define tau to be the relaxation time. Relaxation time. And this is also the average time an electron spends or an electron relaxes. An electron spends between two consecutive collisions with the ions. Okay, consecutive collisions with the metal ions. Okay, which the ions don't move, right? The ions don't move, only the electrons move. Okay, so now let me explain how this relation came. How this relation came. First of all, let us observe the force on the electron. Okay, the force on the electron will be the electric force, okay, Coulomb force. It will be negative E bar. Correct? Negative E bar. So what will be the acceleration? The acceleration will be negative EE divided by m, because force is mass into acceleration, second law of motion, Newton's second law of motion. And suppose the electron is moving with this constant acceleration, okay, for a relaxation time tau, then we can easily calculate the drift speed by using the formula. It is a tau, and that is how the formula Vd is equal to negative E by m tau comes. Force is equal Coulomb force, charge into field, acceleration is force upon mass, speed is acceleration into time. These are three very simple mathematical relations which we have used in 11th standard mechanics. They bring us to this expression for the drift speed, which is average speed, let me remind you, and also relaxation time, which is average time between the successive collisions, and everything else is a constant, E, capital E and M. Have you understood this? Yes. Okay. Now returning to conductivity and resistivity as material properties, because we have earlier said that resistance depends on both geometry and material the material, but not the resistivity. And conductivity being reciprocal of resistivity, it should also not depend on the geometry or the size, but it should also depend on material. That the conductivity, electrical conductivity, which also is the constant of proportionality in the original Ohm's law, so to speak, in this equation, J bar is equal to sigma E bar. That constant of proportionality sigma depends on four things overall. Number one is N. N is defined as the charge carrier concentration. Charge carrier concentration. Okay, it is measured in per meter cube. How many charges are there per unit volume? Number of charges per unit volume. Number of charges per unit volume, that is small n. I will not describe E again. E is the charge on electron. Tau is the relaxation time. Okay, tau is the relaxation time. And okay, let me write it here for the completion, for the sake of completion. E is charge on electron, or any other charge carrier, and m is the mass of electron. Now, because the charge carrier concentration depends on how many free electrons are there, and that depends on the electronic configuration of the material, it will depend on one material to other material, but for the same material it will be constant. So no matter whether you have a rod, a cube, or a very thin wire of copper or iron or steel, N, E, tau and M will be same. And that is why we say that resistivity and conductivity are material properties, whereas resistance is not only material property but it also dependent on the geometry. Okay. Alright. We also define one more quantity called mobility. It is a scalar quantity, and the definition of mobility is the drift speed per unit electric field. Okay, we define it as drift speed per unit electric field. We can obtain this equation. Okay, we can obtain this equation from here. Okay, I will not derive it, but you can see that if it is Vd upon E, it is E tau by M. Okay, E tau by M. So you can define mobility mu, same symbol. We sometimes use mu for permeability, rather more commonly we use it for permeability in the context of magnetic field, but here we are using it for mobility, which is the ratio of the drift speed or drift velocity or its magnitude per unit electric field, or E tau by M. You remember it's SI unit, not very difficult to find. It's meter squared per volt second. You can remember it that way, or you can also remember it this way. Or it will be coulomb second per kg. दोन्ही पैकी कुठलाही चालेल. Okay, be careful in multiple choice questions. That's mobility. So greater the mobility, you expect a better conductivity, right? The electrons are more mobile. Alright, now having seen both the old and the new versions of Ohm's law, please note that Ohm's law is not applicable to all of the conductors that exist there, or rather all of the materials that exist there. And even for conductors, the linear relationship between voltage and current is approximate. Okay, so take the first graph for instance. This is for a very good conductor like copper. Okay, the voltage against current graph is almost a straight line, but as you see, as the values of the voltage increase, you start to see the deviation from the linearity. So this is for a good conductor, a metal. So it is still an approximate relationship, which generally holds good for smaller values of voltages. The actual numbers have not been quoted here, but because they will depend on the material, because every material has a different resistance. Okay, so for a good conductor it is approximately linear, so Ohm's law holds good. Now you know, because we have studied diodes, if I plot the voltage current characteristic for a diode, you will find that it's not first of all commutative, so to speak. That means if we reverse the direction of the current through the diode, then it will behave differently. In the forward bias condition, okay, in the forward bias condition, after overcoming the barrier potential, also sometimes called as knee, if you remember, it's called as knee, and the corresponding value is called barrier potential. After this, the current almost varies linearly with voltage. So this is the ohmic behavior of the diode. Okay, PN junction diode. And when the diode is under reverse bias condition, that means when you reverse the direction of current through the diode, it behaves differently. Okay, it behaves differently, and then you know how to, well, what happens there, okay, under reverse bias and under forward bias. So virtually diode acts as a switch, okay, it acts as a switch. And I would also like you to draw your attention to the scales on the current axis here. In this case it is milliampere here, and here for the reverse bias it is microampere. So the current on the y-axis in the third quadrant here is extremely small, okay, it is almost 1,000 times smaller than the current in the forward bias mode. So you can consider diode to be a good replacement for a physical switch, okay, fine. So but okay, the point is in both the regions the graph is not linear like what Ohm's law predicts, okay. So for PN junction diode, Ohm's law does not hold good. We define a quantity called dynamic resistance in such cases. So we define something called dynamic resistance here, which is change in voltage upon change in current. Instead of directly defining it as V upon I, we can consider it as delta V upon delta I. Okay, with same unit of course. Now, if you take a compound semiconductor like gallium arsenide, okay, if you take a compound semiconductor like gallium arsenide, then its voltage against current behavior is different, okay, its voltage against current behavior is different, okay. Well, observation number 1 from this graph is, for the same current value, there exist two values of voltage. Okay, for the same current value there exist two values of voltage or voltages, and both of them are clearly not equal to one another, and the current is also in the same direction. Okay, now generally you would expect that if I increase voltage the current will increase, okay, but in this case after this peak you see that the current is actually decreasing if I increase the voltage. So that is referred to as the negative resistance region, where even though voltage increases the current actually drops, okay, the current actually drops. Okay, in this case for forward bias we could still say that okay, at least with an increase in the voltage the current does increase, but here in the negative resistance region the current is decreasing with increase in the voltage. Okay, so Ohm's law is not applicable to all class of electronic devices or electric devices that we use, and even for conductors, for good conductors, the relationship holds for smaller values of voltage. Okay, that was the main point. Okay, next, temperature dependence of resistance and resistivity. Okay, now please let me remind you again that the formula that we had derived for conductivity or resistivity here, okay, sigma is equal to Ne squared tau by m. Okay, this was under the assumption that temperature does not change, but what we have found out is that whenever a body has non-zero resistance, okay, whenever a body has non-zero resistance, the conductor will get heated and the energy will be dissipated, okay. And it has also been found that both resistance and resistivity, they depend on temperature, and again for conductors like copper, the temperature dependence of R or resistivity is approximately linear. For nichrome it is almost constant, because if you look at the resistivity against temperature curve of this nichrome, first point it's linear but its slope is extremely small. Look at the temperature scale here, 200 to 800. So if I am talking about, let's say, 200 to 300, then the resistivity is not increasing appreciably. So depending on the material, the resistivity can either increase with temperature, it can remain almost constant with temperature, or for semiconductors the resistivity even may decrease with an increase in temperature. Of course the reasons behind these are hidden in the molecular or atomic structure of the respective substances. For semiconductors, if I increase the temperature, more electrons are available in the conduction band, therefore the conductivity increases, resistivity decreases. Okay, whereas for metals like copper, if I increase the temperature, that amounts to increase in the thermal energy leading to more collisions, therefore the resistance will be increasing for the current to flow, more obstructions will be posed for electric current. Okay, now for smaller values of temperature, I can approximate resistance or resistivity of a conductor as R is equal to R naught into bracket 1 plus alpha delta T. It's an almost linear relationship, rho naught into 1 plus alpha T minus T naught. What is alpha? Alpha is called as the temperature coefficient of resistance. Temperature coefficient of resistance. SI unit per degree Celsius or per Kelvin. Okay, not SI unit, per Kelvin. So R naught T naught or rho naught T naught is the known pair of values. So you know the resistance and or resistivity of a material at some temperature T naught, reference temperature, and how will it change? How will it change with how will R and rho change with temperature? That is decided by this, but don't take this literally as in too seriously. Okay, it will show divergence. Okay, this is only a linear approximation. You may be required to consider more terms on the right side, say quadratic terms or cubic terms, but we will not consider that right now. ठीक आहे, क्लिअर? या फॉर्म्युलावर तुमच्या एक्सरसाइजमध्ये बरीच गणित आहेत. In your exercise there are many problems on this relationship, so you can expect a sum on this in your paper, a sum or a theory question on this. ठीक आहे? Okay. Next. इथे किती सोपं आहे. फर्स्ट डिवाइड बाय रो नॉट. ठीक आहे, फर्स्ट डिवाइड बाय रो नॉट. सो किती काय मिळेल तुला, 1 प्लस अल्फा इंटू टी मायनस टी नॉट मिळेल, बरोबर. देन यू शिफ्ट 1 ऑन दिस साइड, सो इट विल बी रो मायनस रो नॉट अपॉन रो नॉट. So what will alpha be then? Rho, yeah, that was easy actually.
What will be, sir?
That's very easy. Yes, okay. Right. Let's move on. Let's talk about the electrical energy and power. Okay. Now, what kind of energy are we talking about when we say electrical energy? We know that, well, we know electrical potential energy, isn't it? We know electrical potential energy. Okay, we know electrical potential energy, and as electrons move, they acquire kinetic energy. Okay, but because the resistance is non-zero, some portion of this kinetic energy, okay, kinetic energy is transferred to what? Transferred to metal ions. Okay, metal ions which vibrate, and this results into heat. Okay, this results into heat. Okay, and that's why we find the conductor getting heated when you touch it, if the current is flowing. Okay, this results into heat. Now, one very important formula which I want to tell you, number 2, the electrical power formula. Okay, the electrical power formula, P is equal to VI, is a general formula. Okay, this is a general formula. So it works, please note this, it works even when number one, currents are not steady, and even when you have a non-ohmic device. Please remember that. Non-ohmic device means the devices which do not satisfy Ohm's law, V equal to I. Okay, so this is a general formula, and if you remember in the chapter on alternating current, okay, or AC circuits, we have actually used this formula to prove that the average power in a cycle, okay, for a purely inductive circuit or a purely capacitor circuit is 0. There we have used this formula V into I because none of them is an ohmic device. Okay, and currents are also not steady, but this is general formula. Okay, now if we have an ohmic device, then we can get different variants of the power. Okay, we can either get it as V squared by R or I squared. So this formula works only for ohmic devices. Only for ohmic devices. Because here we are using the relationship V equal to IR. Therefore, I is V by R, so V by R into V is V squared by R, or V is equal to IR, so it will be IRI or I squared. Okay, so please remember this. The V squared by R thing or I squared R thing for electrical power is going to work only when you have an ohmic device like a resistor. Whereas if you have an inductor, a diode, a capacitor, let's say a solar cell, anything of that sort, then we have to use the original formula P is equal to Vi, and it's not very difficult to see this. Okay, we know that electrical potential energy is QV. Okay, and what is power? So this is also the work done. And what is the power P? It is the derivative of the work done with respect to time, or the derivative of the energy with respect to time. So it will be d by dt of qv, and if v is constant, then it will be v dq by dt or vi, and that's how this formula comes. Okay, okay. That's electrical energy and power. ह्याच्यात काय डाऊट आहे?
नाही.
Okay. Now the color code of resistors has been omitted from your syllabus, so I'm not taking that, although in our regular lectures we did take that. Okay, the color code, the 4 color code. Okay.
No.
Yes, next. Transmission of electricity at high voltages and transformers. Now we have seen this, that suppose we have a device. Okay, suppose we have a device whose ratings are V and I. Well, it will work well if the potential difference is constant and the current is constant. Okay. Now we never produce electricity in our houses, or whenever we are going to consume the electricity. The sources, the electricity generators are located miles away from that. And therefore we have to use these transmission lines. Okay, we have to use these transmission lines, and it can be proved, that the transmission loss PC, okay, which is I squared RC ohmic, it is given by P squared RC upon V squared. Okay, so the transmission loss is inversely proportional to square of the voltage, and therefore this V is kept very high. Okay, therefore to minimize the loss, the power loss, V is kept very high. Now you might ask the question, but we never use our devices, we never demand our devices to have very high values of voltages. So that's why we have transformers, which we have already covered in the later chapter, right? So In a step down transformer, you lower the voltage. In a step up transformer, you increase the voltage, right? So when I say that V is kept very high, what I mean is, when you are getting the electrical power, let's say from generator to your substation transformer, तिथे voltage खूप जास्त आहे and then you are going to step down it. Okay, so V is kept very high doesn't mean that your device voltage is high. This V is what we step down in transformer later. It is step down using a transformer. Did you get what I explained, or still you haven't understood it? कळलं? मानसी तुला कळालं? Okay. Okay. Next. Acha. Now let's talk about the source which actually creates the electric field in a closed circuit. We call it a cell, right? We call it a cell, and the reaction, the chemical reaction is actually generating the electric field there. Okay. Cool. Now a cell comes with two terms, or two quantities associated with it. First one is the electromotive force and the second one is internal resistance. So what is the electromotive force? Number one, EMF is not a force. First of all, EMF is not a force. Although we say electromotive force, it is not a force. So its SI unit is definitely not Newton. Whereas, okay, number two, a cell has two terminals. A cell has two terminals called positive and negative. Okay, and the potential difference between the two terminals is called as the terminal potential difference. Okay, the potential difference between P and N, okay, between P and N is called as terminal potential difference. Terminal potential difference. Now what is EMF then? EMF refers to V terminal or terminal potential difference in an open circuit. That means no current is flowing. Okay, and the terminal potential difference drops down to a value, okay, to a value which is given by V is equal to epsilon minus IR. So epsilon is the electromotive force, EMF. Again, it's not permittivity, it's epsilon, EMF. And this is where, so this is V terminal in a closed circuit. Closed circuit means the current cannot be zero. So that small r here is called as the internal resistance of the cell. You cannot avoid it. Okay, called as internal resistance, and you cannot avoid it. So if I were to draw a circuit diagram, a simple circuit diagram here, this is the cell, this is the external resistance R, okay, and then I must show an internal resistance here that is denoted by small r, and suppose the current flowing is I. Steady current, cells provide steady current always. And if I apply the Kirchhoff's loop rule, okay, then I'll get epsilon minus IR equal to 0. Okay, and IR is the potential difference across the terminal and therefore across the ends of the resistor. So that is epsilon minus IR. Okay, and that is V, the terminal potential difference. Is this clear? Have you understood this? Okay. Next, if you connect cells in series, okay, if you connect the cells in series, then you have to algebraically add their EMFs and you have to add the resistors. Okay, so epsilon equivalent is the algebraic addition. Okay, algebraic addition of individual EMFs. What do I mean by that? Suppose I have a cell whose EMF is 4 volt, and let's say I have another cell whose EMF is 1 volt, but I connect it in this way, then the equivalent EMF will be 4 plus negative 1, so 3 volts. Okay, so it's algebraic addition. You have to consider how you are connecting the terminals. Okay, fine. But for resistance, it doesn't matter. For resistance, it doesn't matter because it doesn't have any fixed preference to the current. Okay, no matter in which direction the current flows, the resistance always remains the same. So this is the potential difference between the ends A and C. Okay, epsilon minus I. Okay, now in the second case, if you connect the cells in parallel, for two cell combination, okay, for two cell combination, you can arrive at these results, but I'm not going to derive them again. The equivalent EMF for a two cell combination, okay, the equivalent EMF for a two cell combination is very much like the section formula. Okay, is very much like the section formula. If you remember what section formula is. Okay, it's epsilon 1 R2 plus epsilon 2 R1 upon R1 plus R2. It's very much like section formula. And for the equivalent internal resistance of the cell, it's a parallel combination formula that all of you know. Okay, but for a more general case, okay, for a more general case, if you have so many cells, more than two cells connected in parallel, for a general case, you may use these formulae. So R equivalent, the same formula, you know, 1 upon R1 plus 1 upon R2, so until 1 upon Rn, where small r denotes the individual internal resistance of every cell. And for this, for EMF, you have to use this epsilon equivalent upon R equivalent is equal to epsilon upon R1 plus epsilon 1 upon R2, so on till epsilon n upon Rn. So this is simply the junction rule. Okay, this is simply the junction. So yeah, let's move on. Let's go to Kirchhoff's laws. Okay, let's go to Kirchhoff's laws. There are two laws. Okay, there are two laws. First one is abbreviated as Kirchhoff's voltage law, KVL, or loop rule, which is based on conservation of energy, and the second one is called KCL, Kirchhoff's current law, or it is also called as junction rule. And this is based on conservation of charges or charge. Okay, so you remember in any electric circuit, unless a capacitor is there is no accumulation of charges anywhere. The charge has to continuously flow. Okay, and therefore the junction rule works very well. At any junction, there is no occupation or no accumulation. I should have said no accumulation of charges. Okay, it's not like people are standing on a junction, near a junction. Okay, there is no signal here. Okay, there is continuous traffic at that point. Okay, that's Kirchhoff's junction rule. And you also have some conventions here. Okay, you also have some conventions. So let us say this is incoming current. This is also incoming current. This is also incoming current. I'm deliberately showing them in the discontinuous way, but it's actually continuous. Okay, and let these be the outgoing currents. Okay, let me call them I1, I2, I3, I4 and I5. So Kirchhoff's junction rule tells us that the summation of currents is always 0 at any junction. But which summation? Algebraic summation, algebraic addition. So if I consider the incoming currents as positive, I must consider the outgoing currents as negative. Okay, that is what the junction rule tells us. Is that clear? Now let us return to Kirchhoff's loop rule or voltage law. What does that tell us? That tells us that algebraic sum of EMFs and voltage drops in any closed loop is always zero. Okay, is always zero. Now what is meant by that? What is meant by voltage drops? Any voltage drop always has the mathematical form IR. Any voltage drop always has the mathematical form IR, because through resistor the circuit is going to dissipate the energy. That's why when we show load we always show a resistor there, resistive load. What does that mean? A tube light. Okay, it is emitting electrical light energy, right? So it is a resistive device. Okay, the energy is getting converted to light. So everywhere you have to use IR. Please remember, जिथे जिथे रेजिस्टन्स आहे तिथे तिथे व्होल्टेज ड्रॉप होणार. ओहमिक रेजिस्टन्स आहे असं आपण अज्युम करणार, त्याच्यामुळे व्होल्टेज ड्रॉप विल बी करंट इनटू resistance. Okay, now let us try to solve this complicated looking electrical network, and the objective is to calculate the net resistance between the ends A and C prime. Okay, there is a cube like structure here, you can see that, and there are multiple resistors here, one in every edge of the cube, and each resistance, let us say, is R ohms. Okay, each resistance is, let's say, of R ohms, and suppose the battery's EMF is V volt with negligible internal resistance, and our objective is to calculate the equivalent resistance which will consume the same current through this battery when joined across the ends A and C prime. Okay, now one of the main tasks in solving such problems, to determine the current or to determine the net resistance, we should first keep the number of unknowns to be as small as possible, and symmetry is one of the tools to do that. Okay, so let's say we are at A, let's say we are at the point A, and you can see that the paths that our electric current is going to take from A to C prime, they are all symmetrical. Either it can take the A prime path and then followed by everything else, A to A prime, then A prime to D prime, then D prime to C prime, or it can be A to B, or then B to C, or it can be A to A prime to B prime, and then B prime to C prime, and so on. Okay, so you can then distribute the current equally. Okay, you can distribute the current equally in all branches. So if the incoming current is I, then this current I, this current I, and this current I, and at this junction you have to apply this junction rule. Due to symmetry, half of this incoming current will go to D prime, and the remaining half will go to B prime. Okay, now at B prime there are two incoming currents, the one that will come in this direction and the one that will come in this direction. So at B prime again these two will merge and you will get the current I. Same thing will happen at D prime. I by 2 from this, I by 2 from this, so I from this, and same thing will happen from B to C and then C to C prime. Okay, so once the current distribution is complete, okay, then we have to bring in the Kirchhoff's voltage or loop rule. So let us consider any one loop. Let us consider A, B, C, C prime, E and A. Okay, so which loop are we considering? A to B, B to C, C to C prime, okay, C to C prime, then C prime to E, and then back to A. Okay, alright. So how much current is flowing through this resistance? I. So negative IR, it is a drop. Okay, voltage always drops. Minus I by 2R, so IR by 2. Then okay, then plus E, positive because it's energy source, equal to 0. Okay, let me check it again. This is I. This is, oh, okay, wait, I missed one resistance here. Sorry, missed one resistance here. this is I by 2, and then this is again I, right? So minus IR plus E equal to 0, plus E equal to 0. Okay, now if I take IR common and send everything involving IR to the other side, what will I get? 1 plus 1 upon 2 plus 1 equal to E. Okay, so IR into bracket 1 plus 1 upon 2 is how much? Or 1 plus 1 is 2, 2 plus 1 upon 2 is 5 by 2. 5 by 2 is equal to E. Now don't think that the equivalent resistance is 5R by 2. No. What is the original current? The original current is 3R. So if I take 3R here, the current, then what remains will be our equivalent resistance, 5R by 6. Okay, so the equivalent resistance of this cubical network is 5R upon 6. It is actually smaller than each or every individual resistance, that is 5R by 6. Okay, this is a solved problem in your book, but we have again solved it here just to demonstrate how the loop rule and the junction rule are applied. Okay, okay, let's now go to the last topic. The last topic is Wheatstone's bridge. It has many applications including the meter bridge. Okay, but again meter bridge and potentiometer have been omitted, so we will just stick to Wheatstone's bridge for our revision. So Wheatstone's bridge consists of 4 resistors, an EMF source epsilon, and a galvanometer G. Galvanometer is a current detecting device. If current flows, then it will show a deflection. Okay, the balancing condition of the Wheatstone's bridge is that, okay, the balancing condition of Wheatstone's bridge is that no current should flow through galvanometer. No current flows through galvanometer. Okay, and what is the condition for the for balancing using the ratios? The ratio condition is R1 is to R2 is equal to R3 is to R4. That's the balancing condition. So if 3 of these resistances are known, then the 4th one can be very easily calculated. Okay, that is the Wheatstone's bridge balancing condition. Okay, clear? Okay, so that completes our revision of current electricity. If you have any doubts, you can ask, well, not now, you can send them to me.